Hello all, welcome back. We are talking today about elementary processes and reaction mechanisms. So, basically what we're looking at here is that when you look at a chemical equation, let's say for example, whoa, that's not what I want. I want a pencil. For example, nitrogen monoxide plus oxygen gas gives us nitrogen dioxide. Cool. Straightforward, balanced equation, no problem, right? The problem is that equation doesn't tell us what's actually happening to the reactants. How do these things turn into that? So we talked a little earlier about things have to combine at a certain angle, they have to hit with a certain energy, they have to be bumping against each other in the right orientations and everything. So it's not usually a super neat one goes immediately into another. You're going to have some kind of activated complex in between. So for example, for that equation we just talked about, one proposed reaction mechanism would be that two of the nitrogen monoxides, I should use a different color so we can see that a little better here. Two nitrogen monoxides form N2O2 first, right? Two nitrogens, two oxygens. That makes sense, they kind of pair up. And then my N2O2 combines with the oxygen, and that's going to give me 2NO2, so that's where the extra oxygens come in. So if I were to look at the net reaction here, I have N2O2 on this side, and I have N2O2 on that side, so they would cancel out. I'd end up with 2 NOs plus O2 give me 2 NO2. That's exactly the reaction we wanted. But it happened in two steps and created this weird N2O2 thing, which doesn't show up in the net reaction. That would be kind of like our activated complex kind of idea. It's some chemical that we formed during the process of making it, which doesn't actually exist in the net equation. It's an in-between. We're going to talk about that in a second. It's got a special name. So, those steps are called elementary processes. The smallest steps that could be taken in a chemical reaction. Now, all those steps together we call a reaction mechanism. The mechanism by which the reaction happens. What are the steps in making these things work together? So that N2O2, that substance that appears as a product in the reaction mechanism, but doesn't show up in the actual net reaction, we call that an intermediate. So it's part of the reaction mechanism, it's part of how the chemistry happens, but it's not part of the equation. It's just like an in-between. We call those intermediates. So here's our example here. We got NO2 plus carbon monoxide gas forms nitrogen monoxide and carbon dioxide. There we go. So one proposed reaction for this would be like this. Two NO2s combine to make an NO and an NO3. So basically it's just like a one oxygen transfer. So they're going to collide oxygen ends first, and one of those oxygens is going to be handed off. NO and NO3 are formed. And if you look up here, I see NO in my net equation, so there's a good chance I'm not going to use that up in my next step. I need that to hang around. But I don't see NO3. So I'm probably going to have to do something with that NO3. And look, here it is. I'm going to use up that NO3. And what are we going to use it with? Well, what's up here? What's on my reactant side that I can use? I've already got some NO2s, so maybe the carbon dioxide or monoxide. So if I combine those two, what could I make? Well, I mean, the oxygens could transfer again, and I could be left with NO2 and CO2. So if we look for our actual net reaction here, I have one NO2 on this side, so I can cancel one on that side. My NO3 is an intermediate. It was formed in one step, destroyed in the next, so we're going to cancel that one out. And what am I left with? I've got NO2 plus carbon dioxide gives me nitrogen monoxide plus carbon dioxide. And hey, look, that's my exact reaction that I wanted. Sometimes you get catalysts, right, in chemical reactions. We talked a bit about catalysts and what they do and stuff like that. But what would that look like in a reaction mechanism? So, we got a reaction here. Two ozones form three oxygens. So it looks like a real easy equation, right? Two ozones, two O3s give me 3 O2s. Well, that's easy enough. Just like transfer, like have 2 ozones collide and 2 of the oxygens break off, right? And that would form an extra O2, and then I've got 3 O2s and life is good. I would have, would look like this if I were to draw it. So these ones would collide here. I would break the bonds here and here, and I would be left with oxygen, oxygen, oxygen. Look at that. 2 ozones became 3 O2s. Fantastic. Problem is, that reaction is real slow. The odds of them colliding at just this orientation and in just this direction and with the right amount of speed, it just doesn't really happen. Ozone does not break down that easily on its own. So if you were actually to try and do this reaction, we add a catalyst to it. Turns out, if you add Cl2, again, these numbers should mostly be subscripts, to the ozone, holy smoke, stuff just starts falling apart. Now, what's going on there? We need a reaction mechanism. Turns out in step 1, the chlorine rips one of the oxygens off. So you get chlorine monoxide, oxygen gas, and a loose chlorine. Eeh. That's not really a very stable compound, so you're not going to expect that to stick around. We're going to use that somewhere. In our next step, ozone breaks down into O2 and loose oxygen. Again, not really a super nice substance. We're probably going to use those up. So why don't we do that? We're going to use our oxygen, we're going to use our chlorine, and we'll use the intermediate, because we know chlorine monoxide doesn't show up anymore. Let's use all of these things together. 2 Cl's and 2 O's. So I've made Cl2, and I've made O2. Now, let's look carefully here. I'm going to erase all this. Yeah, I'll erase these annotations so we can see a little more clearly what we're talking about here. 2 chemicals I want to look at very closely. First one is the ClO. We make it in the first step. We destroy it in a later step. That's the only place chlorine monoxide, or ClO, shows up anywhere in this equation, which means ClO is an intermediate. It is formed in one step, destroyed in another, as part of the reaction mechanism. You could also say that atomic chlorine and atomic oxygen would all be intermediates. Those things are all formed in one step and destroyed in a later step. They never show up in the actual equation. What about chlorine, though? Chlorine gas we start with as a product. And if you look at the end of the equation, it's still there. We started with chlorine, and at the end, we still had chlorine. So they cancel out of your net reaction. You don't actually see them. But could you do this reaction mechanism without chlorine? Well, obviously not. We couldn't form this or this without chlorine. It's the reason why this reaction can happen. You need chlorine there to make it work. So we call that a catalyst. Catalysts are substances that start out in the chemical reaction as a reactant, and they finish up as the same substance. It's still chlorine gas. So they finish as the same substance in the end as a product. It's needed for the reaction mechanism, but not actually used up. That was covered by my little thing there. So it's not actually used up. Yeah, I'll leave. Let's go back. There we go. So, needed for the reaction mechanism, not actually used up. We call them catalysts. You can't have the reaction without them because they're used in all of our intermediates, but they show up at the beginning and they still show up at the end. They haven't changed. I destroy it and then I make it again. Last thing we're going to chat about today is the rate determining step. So reactions have speeds, right? They go at a certain pace, and there's all kinds of different things that determine that pace, you know, with concentration or temperature, catalysts, stuff like that. Whichever step, so you've got this reaction mechanism now, whichever step, whichever elementary process is the slowest, so whichever individual step has the slowest reaction rate, will be what we call the rate determining step. So that means it's a really, really important part of the mechanism because it's going to tell you how fast the entire reaction happens. All the other steps have to wait for it to happen. So however fast that one rate determining step is, that's how fast the whole reaction is. Think about a fire drill, right? So we got all these rooms in school, the bell goes, oh no, fire, everybody's got to go. So we all book it outside, and you got to send a runner to report to the principal or whoever's in charge, right, to say, yeah, our class is here, we've checked in, before you get back into the building. It doesn't matter how fast my class is if my neighbor's class goes for a casual stroll. So we're looking for, like, fire drill is a really good metaphor for this. The next door neighbor's class would be our rate determining step. Everyone in the building waits for them if they're the slow pokes that are just slowly walking their way out of the school. And instead of running to go see somebody and sign in, they're just like, yeah, I'll get there when I get there, taking their time. So that slow classroom slows down the entire fire drill. So we're all waiting for them. Same idea, with a reaction mechanism, right? If step 2 here was really slow, it doesn't matter how fast the other steps are. Step 1 can make, step 3 can use up oxygen as fast as humanly possible, but it's waiting for step 2 to make them, right? And it can't use up the CLO that's made in step 1 because it doesn't have enough oxygen yet, because we're waiting for step 2. So the entire thing depends on step 2. However fast step 2 is, the entire rate of the reaction depends on it. Everyone else waits for them. So that's our rate determining step. We're going to be using that in future lessons when we talk about how can we mathematically calculate how fast a reaction will go, because one of the important things is you got to know which step makes it fast or which step makes it slow before you can start using some math on that. So thanks for watching the lesson, guys. That's going to be it for today, and I will see you next time.